ఇన్వైట్ చేసుకుంటాను. చూస్తాను ఈ సైడ్ బాగా సపోర్ట్ చేయడం బయట రోజు చెప్పేస్తాను. స్టార్ట్ చేయమ్మా గీతమ్మా. Good morning, student friends, and also thank you organizers again for providing me this slot and taking up huge and serious activity for the benefit of the students. And student friends, we have discussed earlier all the other chapters like fluid properties and pressure and hydrostatic forces on surfaces, and afterwards we have discussed the fluid kinematics and also fluid dynamics and applications of Bernoulli's equation. So we have almost covered almost 75% syllabus, and we have three important chapters. One big chapter is analysis of fluid flow. That is one chapter. Other than that, we have another two chapters. Still we have 4 classes, including this class. And analysis of fluid flow I will be taking as it is an important chapter, and it attracts a maximum number of gate questions. And we'll spend more time on analysis of fluid flow, which is easy provided you understand the concepts and remember the equations, etc. And the other 2 chapters are notches and orifice and boundary layer theory and lift and drag. So this is the syllabus, and if time permits, I will also give 100 set of questions, and I will try to answer on the last day itself. So this is the schedule, and I hope you are following the earlier topics, and we have placed everything in website, the PPTs, etc. Yesterday I have seen that everything is made available in the PPT of JNTU Anupur website. So now the chapter is analysis of fluid flow analysis, and we have Reynolds experiment. Analysis of pipe flow means, so once again each and every chapter is very important, but this chapter again we need the concepts and discussions and formulae of all the previous chapters. So based on that it is easy for you to understand this chapter. So analysis of pipe flow and existence of pipe flow and what are the different types of flow, expecting all these things. And the other one is Reynolds experiment. So Reynolds is the name of the inventor, name of the investigator who has invented the procedure for identifying laminar and turbulent flow. For example, so this is Reynolds apparatus. So if you see here, this is the water tank here, and it is having water. And this is again a small tank here. If you see here, this is the color solution. It is that some color solution here. And this is the horizontal glass tube. The glass tube is horizontal. This is a horizontal transparent glass tube, and so that you can visualize what exactly happened in the glass tube. and this is a regulating wall. Regulating wall here. This wall, it can control the flow of water which is coming out from the horizontal glass tube. So Reynolds has taken up this experiment for identification of a type of flow. As you know, we have two types of flow, laminar flow and turbulent flow. And for example, if you see here what happens when valve is open here, let us say when the valve is open, then what happens here? The water from the tank here, the water from the tank, so it flows slowly and steadily and comes out into the atmosphere. For example, consider three cases here when valve is slightly open and valve is half open and valve is full open. In other words, when the water is flowing with this low velocity, when water is flowing with high velocity and very high velocity. Take three aspects here. So three are very, very important. Let us say the first stage, when the valve is open slightly. So then what happens here? The water which is there in the big tank, so it starts moving into the glass tube and finally into the atmosphere. Then at the same time, this is a small tank here with the color solution. So I introduce this color solution here. This color solution, the purpose is to know the movement of water. So because the water is a transparent and the glass is a transparent, you cannot visualize what exactly happened when the water flows through the horizontal tube. And this is a color solution. This color solution is introduced here to know the movement of fluid in the horizontal pipe. So for example, when the valve was slightly open and when the water is allowed to flow into the tank, at the same time when the color solution is injected here, so what exactly happened? So this is the figure. So this is the movement of dipole here. So if you see here, this is straight. This is straight. So that means when the fluid velocity was very low and when it is flowing through a small diameter pipe, what exactly happens here? So the movement of water here, you can visualize the dipole, it moves steadily. So if you see here, it moves steadily and stable and without mixing here. If you see here, this decline is a dipole. So the color solution, it is not moving from the top to bottom or bottom to top. So it is moving straight here, straight, stable and without any irregularities and without intermingling. So this particular type of the flow is called laminar flow. So you can expect a laminar flow in nature when, if you consider the velocity of the water very low, when the water is flowing through a small diameter pipe with a low velocity. That is an example for laminar flow. So you can see here, this is the straight filament and which has not shown irregularities, which has not. So this is all important for objective questions here. Entire theory, what we are discussing now, it will be helpful for you to answer the objective questions of GATE examination. Yesterday or day before yesterday, from the last classes, we have observed that, and some of the questions are very critical and some of the questions are very important and which requires your understanding capacity of the subject also. And this is a laminar flow. This is straight and stable and flows steadily without any mixing. So I can say it is a laminar flow. So at this stage one, let us say when you have opened the valve a little more. So now the valve is open. So the purpose of the valve is to regulate the flow of water in a horizontal tube. So now the valve is opened further. So this is the valve you can see here. Now it is opened further. Then what happens? In other words, you have increased the velocity of the water which is flowing through the horizontal glass tube. So now the water is moving with velocity, with high velocity. Now at this stage, again inject a color solution. Inject color solution. Then what happens here? And when there is a slight increase in the velocity of the water, you can observe the movement of filament here. So this movement here, if you see here, and this is a curvilinear variation. This is not straight here. If you see here, this is the laminar flow is straight. Now this is not straight here and this is coming up and down here. Again the movement is not stable and movement is irregular here and again there is no diffusion here. So this is intermediate type of the flow and this you can say it is a transition. So transition flow is a flow in which the laminar flow changes from, in which the flow changes from laminar to turbulent. So now we have discussed the laminar flow and also transition flow. So transition flow is the transition state. Name itself is very clear. It is a transition. So it is a state wherein the flow is changing from laminar to turbulent. So this transition state you can see here, and this is moving up and down, and this is moving up and down, and again it is coming out with velocity. So this particular stage is called transition. Now we go to the final stage when the valve is fully opened. When the valve is fully opened, when the water is coming out freely and with high speed into the atmosphere. Then at the same time, suppose if you inject a solution here, then these irregularities, if you compare with the transition flow, so these irregularities became more intense here. If you see here, this is more intense, and finally it is diffused over the entire cross section. It is diffused over the entire cross section. So you can see here, this is a diffused filament, this is wavy filament, and this is dye filament. So when it is diffused completely, when it spreads over the entire cross section, so that is called turbulent flow. So now we have discussed about laminar flow, turbulent flow, and transition flow. So these terminology is very important, and you can easily remember what is meant by laminar flow and what is meant by turbulent flow with the help of these neat sketches. And I have also taken these sketches from a standard textbook. And Modi and Seth and Bansal are good books, and we have Aurora is also there, and the material from ACE and the material from FML HM by the famous textbook. And so this is crystal clear about laminar flow and turbulent flow and transition flow. So this is the experiment. Based on that, Renal has experimented that to find out the existence of different types of flow. So laminar flow, transition flow, and turbulent flow here. Then we have Reynolds number here. Reynolds number. So Reynolds number is ratio of inertia force to viscous force. So here we can find out different types of flow, and we have the equation here. Reynolds number is inertia force to viscous force. Reynolds number is inertia force to viscous force. So inertia force you can obtain and viscous force you can obtain. So inertia force is as per Newton's second law you can obtain, and viscous force you can obtain. We have a Newton's equation of viscosity, tau is equal to mu into d by dy. So the viscous force is CSS multiplied by area. And the inertia force is mass into acceleration, Newton's second law of motion. So this is the Reynolds number is very important. It will be, and based on that we have a number of gate questions in that. Reynolds number, type of the flow, etc. All the equations what we are discussing now, you try to remember those equations and what is the concept behind that and how will you arrive the equations. Not necessarily to derive the equations, but the concepts, what are the concepts you have used for arriving these equations is also important. And we have inertia force to the viscous force is Reynolds number. Inertia force to the viscous force is Reynolds number. When the Reynolds number is less than 2000, it is laminar flow. When it is greater than 4000, it is turbulent flow. So I mean to say that I have written this LFE, this is laminar flow, and the equation for finding out Reynolds number, if you take the viscous force is the shear stress into area and inertia force is the mass into acceleration, and if you convert to the dimensional form, so the final equation is Vd by kinematic viscosity. Kinematic viscosity is different from dynamic viscosity. This is very important chapter, and also EG chapter provide the equations and background of the equations. So the Reynolds number is inertia force to the viscous force, and less than 2000 in laminar flow. And when the Reynolds number is, so this is the number here. So number is obviously there should be no units here. Sometimes it will be confusing. So it has given Reynolds number, some units. And it has no unit here. For example, you see here. So this is a kinematic viscosity. So kinematic viscosity, what is the unit of kinematic viscosity? It is Stokes or meter square per second. And the velocity meters per second. The d is the meters here, meter square per second by meter square per second. The Reynolds number has no unit here. So when the Reynolds number is kinematic viscosity, as you know, it is nu, which is also equal to mu by rho. That means dynamic viscosity by mass density Dynamic viscosity by mass density is equal to kinematic viscosity. Dynamic viscosity by mass density is equal to kinematic viscosity. So less than 2000 is laminar flow and more than 4000 is turbulent flow. Then we have another famous equation called Darcy-Weisbach equation. Darcy, and between 2000 to 4000 it is transition flow. When the Reynolds number is less than 2000 it is laminar flow. When it is more than 4000 we can say it is turbulent flow. In between 2000 to 4000 it is a transition state. So transition flow is 2000 to 4000 and there is one famous word called critical velocity. So important for object type. What is the critical velocity? Critical velocity is the velocity for which the water flow changes from laminar to turbulent. Very, very important definition. You can also note down the critical velocity is the velocity at which the flow changes from laminar to turbulent. So when the flow is not neither laminar nor turbulent, in between the flow, that is the velocity of the in-between flow, that is in-between flow means between laminar and turbulent flow, the velocity is the critical velocity. So critical velocity is the velocity in which the flow changes from laminar to turbulent. Important objective question. So next equation is Darcy-Weisbach equation. Darcy-Weisbach equation. So HF is equal to FLV square by 2CD. There is a famous equation. I will give one or two steps to how to arrive this Darcy-Weisbach equation. Very famous equation for finding out head loss due to friction. And just follow the concept of friction here. So now take a circular pipe here. Take a uniform circular pipe. Uniform pipe means the diameters are same. So when the diameters are same, obviously the velocities are same. So indirectly in the problem he mentions, normally he mentions the diameter is same. Diameter same means you can as well take V1 and V2 are same. For example, see here as the diameter is same, so you can take that the velocities are same. So V1 is equal to V2. V1 is equal to V2. Then, so you have the pressure here, and how exactly, let us say if you see here, this is the friction force here. When the water is moving in a pipe in this direction, in the forward direction, and you can expect that there is a friction between the pipe surface and the fluid here. So the friction always acts in the opposite direction. The frictional stress or frictional force or friction always acts in the opposite direction here. So because of the friction between the pipe material and the water, and there will be always friction and which opposes the movement of forward flow. For example, you see here, so this is the friction force, and this is moving towards this direction. So this is the movement moving towards this direction here. When this is moving here, and friction is opposing the flow here, and this is the friction is due to the surface and the fluid here at the bottom side and the top side around the circumference, and the top side also between the surface and the fluid, and between the pipe surface and the fluid, and also it is due to the between the friction between the individual fluid particles. Most of the students they think that the friction is only between the pipe material and the fluid. So this movement, the forward movement is also opposed by the friction between the individual fluid particles when it is sliding over the other. So friction between the fluid particles, and the surface, which are all responsible for getting resistance to the forward motion, that is due to the friction. Then how will you quantify this friction here? That is Darcy-Weisbach equation. Darcy has given a procedure for arriving the head loss due to friction. So now you have pressures here. Apply Bernoulli's equation here. So when it is a pipe here, when it is a pipe having uniform diameter, the velocities are same here, and you can take the datum straight away along the center line of the pipe. Then Z1 is equal to Z2. So datum heads are same and velocities are same. Then what is the Bernoulli's equation here? Bernoulli's equation is As you know, P1 by W we have discussed yesterday. P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2, and take real fluid here and plus HL. So HL is a loss of head. HL is a loss of head here. When the flow is flowing from one side to other side, the loss is mainly due to the friction. In other words, you can say that when the length of the pipe, if you consider the section 1 to 2, so when the length of the pipe is more than 1000 times the diameter of the pipe, you can say it is a long pipe for which friction is the major loss. So obviously for short pipes need not consider friction loss. It is required only for the long pipe. So long pipe means when the length of the pipe is more than 1000 times the diameter of the pipe, you can say that the friction loss is a major loss, and you can take the friction loss as a major loss. So for the case of real fluids, when the pipe is a long pipe, now the pressure head or total head at 1 is equal to total head at 2 plus losses, and the loss due to only friction, HF. So P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2 plus HF. So we have a P1 and P2 both are same, and P1 P2 are not same, V1 V2 are same, and Z1 Z2 are same. Then what is the equation? P1 by W plus 0 is equal to P2 by W plus 0 plus HF. The losses are only due to and due to friction. So HF is equal to P1 by W minus P2 by W. The head loss due to friction is equal to P1 by W minus P2 by W. And suppose if you simplify that, the final equation is HF is equal to FL V square by 2GD. FL V square by 2GD, where F is the coefficient of friction. Normally it varies from 0.02 to 0.03. So the equation for HF is FL V square by 2GD, Darcy-Weisbach equation. So HF is the head loss due to friction, F is the coefficient of friction, L is the length of the pipe, and V is the square of the velocity, and 2, and G is the gravity, and D is the diameter. So if you see in the figure here, so this is L is the length of the pipe from section 1 to 2, and D is the diameter of the pipe, FL V square, and V is the velocity of the water which is flowing through the pipe, and G is the gravity, D is the diameter of the pipe, everything is known, and F is the coefficient of friction. So F is the coefficient of friction, L is the length of the pipe, V is the velocity, and D is the diameter. So F is the coefficient of friction which varies from 0.02 to 0.03. Some of the textbooks is also taking 4F LV square by 2GD. Both are correct. But F is equal to 4F is equal to, it varies from 0.02 to 0.03. Then we have another two equations for arriving velocity of the flow. So you have two equations here for arriving the flow. And Church's formula, V is equal to C root RS. Famous equations here for velocity. Church's formula, V is equal to C root RS, and Manning's equation, V is equal to square root of 1 by N, R to the power 2 by 3, and S to the power 1 by 2. These two are also equations. Based on that, you can find out velocity. Other equations for finding out the velocity. Church's formula, which is equal, so this V is the velocity here. The capital V always represents velocity, and C is the Church's constant. It is between 50 to 60. Church's constant, C represents Church's constant, and R is hydraulic mean radius here. R is hydraulic mean radius, which is equal to A by P. We will be getting more about hydraulic mean radius in our water resource engineering. But meanwhile, hydraulic mean radius means A by P. A is the area of cross section, and P is the perimeter. And hydraulic mean radius for the circle, let us say the pipe is running full, P is the wetted perimeter. In the hydraulic mean radius, the definition of R is equal to area by perimeter. That perimeter is wetted perimeter. Let us say pipe is running full. Then what is hydraulic mean radius? Pipe is running full means it is completely wetted here, and R is equal to A by P, and A is the cross section area, and P is the wetted perimeter. And the cross section area is pi d square by 4, and the perimeter, as you know, it is pi d. So pi d square by 4 by pi d, and the answer is d by 4. So the hydraulic mean radius for the circle pipe, when the pipe is running full of diameter d, then r is equal to d by 4. Area is pi d square by 4 and p is the wetted perimeter. Then we can find out r without any difficulty. Then the other one is s here. S is the longitudinal slope. S is the slope here. So this HF represents head loss due to friction. Head loss due to friction. And that divided by L is the length of the pipe. L is the length of the pipe. So HF is the slope here, head loss due to friction, and L is the length here. So we can find out the slope here. Slope is equal to, answer slope is equal to head loss due to friction by length of the pipe here. So that we can find out R and S, and C is given constant value. Suppose if we sometimes may not give the value of C, you can take 55. Normally the H is constant is 55. So you can take the value of 55, and so that you can find out the value of velocity. The other one is Manning's equation. So Manning's equation is equal to 1 by n into r to the power 2 by 3 into s to the power 1 by 2. Again depends on r and s value. R is hydraulic mean radius and s is the slope here. And 1 by n. So 1 by n is called Manning's coefficient. Again I will be giving the 1 by n is Manning's coefficient. C, each is constant. So we will be giving the values of 1 by n and c, and you can find out r and s, and you can also find out the velocity as per Church's formula and velocity as per Manning's equation also. So try to remember the important equations I have given up to now. Reynolds number is Vd by nu, and when the Reynolds number is less than 2000, it is laminar flow. It is 4000, it is turbulent flow, and between 2000 to 3000, it is a transition flow, and the velocity is the critical velocity at which the flow changes from laminar to turbulent. And Darcy-Wisbach equation, try to remember that it is HF is equal to FLV square by 2ZD, and hydraulic mean radius is R is equal to A by P, S is equal to HF by L, and Church's formula V is equal to C root RS. So V is equal to C root RS, C is the Church's constant, R is hydraulic mean radius, and S is the slope here, HF by L. And Manning's equation V is equal to 1 by n, r to the 2 by 3, s to the 1 by 2, where 1 by n is Manning's coefficient. So try to remember these equations. These are all very, very important for doing the objective questions. In addition to the Benner's equation, continuity equation, etc. Yeah. So then when the length of the pipe is more than 1000 times the diameter of the pipe, so the friction loss is a major loss. Friction loss is dominating, and you can take only friction loss. Friction loss as per Darcy-Wisbach equation, HF is equal to FLV square by 2ZD. That you can take and you can use that as a major loss when the length of the pipe is more than 1000 times the diameter of the pipe. Then head loss due to sudden enlargement. The other losses. And suppose the pipe is a short pipe. The pipe is a short pipe. We have number of losses are there. I am listing it out now. So one is head loss due to sudden enlargement. So when the pipe is initially having diameter D1, again suddenly enlarges to D2. Suppose if you see here, this is pipe is having diameter D1. So this is D1 here. This is D1 here, and this is suddenly enlarged. So this is D2, section 1 and section 2, wherein the velocity, the diameter is D1 here, and the velocity is D2 here. So this is D1 and this is D2. So the diameter, if you see here, this is the pipe, normally it is coming, again it is suddenly enlarged, not gradually here, this is sudden enlargement. So when there is sudden enlargement, what happens to flow here? The flow goes in this direction, and you can expect a backward flow also. This is the forward flow. So you see the velocity here, is V1, and the velocity here is V2, and the water is flowing like this. So the velocity V1 and velocity V2, the water is flowing like this, and this is the pressure force, and this is the pressure force here, and the pressure force here is P1A1, and pressure force here is P2A2, and the loss here, major loss here is loss due to sudden enlargement. So the velocity at point 1 is known and the velocity at point 1 is known because diameters are different. We have a different velocities here and different pressures are here. And you have losses here. Obviously, as losses are here, this is a backflow here. This is not this space is not completely utilized. So the efficiency is less here, and we have backflow here. So for this case, again apply Bernoulli's equation. You can arrive the equation. Whatever the derivations normally requires the famous equations, Bernoulli's equation and continued equation. So you can solve any problem of fluid flow if you know how to use Bernoulli's equation and continuity equation or discharge equation. So now when the head loss due to sudden enlargement, the equation is V1 minus V2 square by 2G. Try to remember this equation here, which is very, very important. Head loss due to sudden enlargement is velocity V1 minus velocity V2 whole square by 2Z. So V1 is the velocity of the water before enlargement and V2 is the velocity of water after enlargement. The other is head loss due to sudden contraction. This is also major loss. All these losses are minor losses. All these losses are need to be considered for sharp pipes, or you can say these are all minor losses. The values are less here. Then the other one is head loss due to sudden contraction. So now the water is flowing here. So it is suddenly contracted. So this is the pressure force here is P1A1. This is the diameter is D1 here. The diameter is D2 here. And the pressure force here is P1A1. And the pressure force here is P2A2. Then what happens here? Now this is reversed here. In other case it is enlargement. It is now contraction. So this is a pipe here having a diameter D1. And if you see here, this is suddenly contracted. So pipe loss due to sudden contraction. So this is suddenly contracted here to D2. This is D1 here, then this is D2 here. So when it is suddenly contracted, entire the space is not effectively utilized here. Again there is a backflow here. Again there is a backflow here. So then what is the loss due to sudden contraction? For example, this is also loss due to sudden contraction. You need to consider in the total head losses. We have discussed the head loss due to friction, head loss due to sudden enlargement, and head loss due to sudden contraction. So the head loss due to sudden contraction, if you see here, the flow is from 1 to 2. The pressure force here, which is acting in this direction, and the pressure force here, P to 8, which is acting in this direction here. You can apply Bernoulli's equation between points 1 and 2, and the loss is mainly due to the sudden contraction. We can find the equation is K V square by 2Z. K V square by 2Z. So this is actually V2 square, K V2 square by 2Z. K V2 square by 2Z. K V2 square by 2Z. So this is why I stressed V2 here. So this V2, head loss due to sudden contraction, need to take velocity after contraction. So we have velocity V1 and velocity V2. Velocity V1 and velocity V2, you need to take up the velocity after contraction. That's why this is, I have given V2 here. K V2 square by 2Z. V2 is the velocity of contraction. Some of the students, they are confusing and they are taking V1. So it is required to take only V2. So normally if the value of K is not given, you can take it is 0.5. Sometimes the value of K is not given, CC or K is not given, you can take 0.5. So head loss due to sudden contraction is 0.5 V2 square by 2Z. You can scientifically take when there is absence of data, you can take the value of K is equal to 0.5 if CC is not given. Then K value, suppose in the value of CC is given, CC is called quotient of contraction. CC is called quotient of contraction. So the 1 by CC minus 1 whole square. 1 by CC minus 1 whole square is K. So the quotient of contraction, again it is between 0.6 to 0.7, approximately 0.6. So when the head loss is not given, I mean, when the value of K is not given, you can take 0.5. When if CC is given, let us say, CC is a quotient of contraction, CC 0.6 to 0.7, you can find out the value of K and you can substitute here for arriving head loss due to shunt contraction and entrance loss. Entrance loss, when you consider the entrance loss, let us say, yeah. Like, let us say this is a pipeline. I will come back to that, the various pipes and different diameters, but only for entry and exit loss, I want to take this figure. So when the water on the tank, when it is entering here, so when the water is entering here, there is entry loss. So when the water is exiting, when the water is entering into the tank B, this is exit here. We have entry here, we have exit here. So entry loss and exit loss. So entry loss is 0.5 V square by 2G. So this V, what is this V here? The velocity of the water which is entering the pipe. Suppose if we might have confusion that what should be V here, V1, V2, etc. So take the velocity of the water which is entering the pipe is V here. 0.5 V square by 2G. Again exit loss. And take the velocity of the water which is entering into the other tank, that is exit. So find out the velocity of water is exit. So that is V here. So this V and this V are different. So this V, if the velocity is same, then we can have same velocity at the entrance and exit. But the velocity is not same for different pipes if they are connected, let's say. So here, this is V here. So 0.5 V is the velocity of water which is entering. And G is the gravity, 9.81 meters per second square. Again exit loss. So exit loss is V square by 2G. So the water when it is exit, take the velocity of the exit. So that is V square by 2G. So all these equations are very important. So you may not get bend loss and head loss due to gradual contraction enlargement, but all the above equations you should be in fingertips. For example, when you do the actual problems, normally in the gate examinations, it is required to remember all these small equations. Otherwise, it is difficult for you to solve the questions of gate, particularly on pipe flow. Again, you have bend loss. Sometimes pipe is having bend loss. So bend loss, you can remember the equation. Sometimes it may require kV square by 2Z. Bend loss is kV square by 2Z. And again, head loss due to gradual contraction enlargement. Head loss due to gradual contraction enlargement, which is equal to K into V1 minus V2 whole square by 2Z. So when it is gradual, so this is sudden. So the enlargement is sudden, the contraction is sudden. So you don't confuse with this and this. This is sudden enlargement, sudden contraction. This is gradual. Gradual contraction enlargement, which is equal to K into V1 minus V2 whole square by 2Z. K into V1 minus V2 whole square by 2Z. That is the equation. So all these equations are very important. I try to remember all these equations. Without these equations, without remembering these equations, it is difficult for you to solve any problem. Okay. So there is a relation between Fn or N. So Rn is Reynolds number. Rn is Reynolds number. Rn is Reynolds number. So when it is for laminar flow, when the Reynolds number is less than 2000, and this is important object type, this relation, and this relation, so for example, F is equal to 64 by Rn. Rn is Reynolds number less than 2000. So when the laminar flow, when the flow is laminar, the value of Reynolds number is less than 2000, then the relation is F is equal to 64 by Rn. Rn is Reynolds number. For example, when the flow is turbulent, so that means when the Reynolds number is more than 4000, F is equal to 0.316 by Rn to the power of 1 by 4. 0.316 by Rn to the power of 1 by 4. Need to remember this equation here. For example, at the end of the chapter we will have gate questions. In the gate questions, we have questions on or problems on relation between F and R, and you need to find out the flow is laminar or turbulent. So first find out Reynolds number. Reynolds number is VD by nu. So based on the Reynolds number, you can decide whether the flow is laminar or turbulent, and use the appropriate equation. If it is a turbulent flow, you use this equation 0.316 by R into the power of 1 by 4 and find out F. And this was the question which was posed to me when I have attended interview of assistant professor in J.N.T. Kakinada. It's a government college, J.N.T. Kakinada, University of Engineering Kakinada. When I attended interview at J.N.T. Hyderabad way back, and experts, we have experts in the interview board, and one of the experts, he has asked me, give me the relation between F and Rn when the flow is turbulent. At the time I mentioned clearly that the turbulent flow, you can say that when the Reynolds number is less than 4000, and the relation between F and Rn is F is equal to 0.316 by Rn to the power of 1 by 4. I have given the correct answer. So all these equations are necessary for you to do the problems. So let us take one or two problems or 3 to 4 problems on that. One problem, let us say, find the head loss. More or less these type of problems. Why I have taken some of the problems during discussion, because we have a more or less such type of problems even in gate examinations. So find out the head loss due to friction in pipe diameter 25 centimeters. This problem is on head loss due to friction. The diameter is 25 centimeters and length is 60 meters, and water is flowing at a velocity 3 meters per second, and he has asked me to find out the head loss due to friction using Darcy's equation and changes formula. So he has given the data and he has asked me to find out the head loss due to friction using Darcy's formula and changes formula. Darcy's formula, we have, as you know, equation is FLV square by 2ZT, FLV square by 2ZT, and changes equation, as you know, it is V is equal to C root RS. So we should know the equations here. HF is equal to FLV square 2ZT and V is equal to C root RS. Then, so the velocity into so for the problem, he has given changes constant C is equal to 55. C is equal to 55. And kinematic viscosity is 0.01 Stokes. So again, he has given kinematic viscosity in Stokes. So 0.01 Stokes means 0.01 centimeter square per second. 0.01 centimeter square per second. So then, find out the Reynolds number. So for the problem, he has asked to find out head loss due to friction. For finding out the value of F, he has not given the value of F here. You need to find out F. For that, so takes the equation Reynolds number, which is equal to Vd by nu, Vd by kinematic viscosity. So the velocity is, you can take the velocity 3 meters per second, and d is the diameter. So convert this d into meters here, 0.25. So the diameter, the velocity 3 meters per second, and diameter is 0.25, and that divided by nu, kinematic viscosity. Kinematic viscosity again 0.01, it is in Stokes. So 0.01 centimeter square per second, 0.01 centimeter square per second. Then convert into meter square per second. So 0.01 into 10 power minus 4 meter square per second. So now Vd by nu, so V is 3 and diameter is 0.25 and viscosity is 0.01 into 10 power minus 4. So the kinematic viscosity is 75 and 4 zeros, 750,000. 750,000. And F is equal to 0.0107. So when F is 0.010, so this is, so now the flow is turbulent flow. When it is more than 4000, so Reynolds number is Vd by nu, 75 and 4 zeros. So when the Reynolds number is more than 4000, what is F here? F is equal to 0.316 by Rn to the power of 1 by 4. And use this equation, F is equal to 0.316 by Rn to the power of 1 by 4, where Rn is 750,000. So F is equal to 0.316 by 750,000 to the power of 1 by 4. So if you solve that, F is equal to 0.0107. Very simple. So find out the Reynolds number. If the Reynolds number is less than 2000, use this equation. When it is more than 4000, use this equation, 64 by Rn, or this one. And when this Reynolds number is more than 4000, then use, it is required to use equation F is equal to 0.316 by Rn to the power 1 by 4. F is, and Rn is 75 and 4 zeros here, and from that F value is equal to 0.0107. Then we have the equation here, Hf is equal to Flv square by 2Gd. F you have a 0.0107, and L you can see here, L is 60 meters, length of the pipe is 60 meters, and the velocity has given, velocity 3 meters per second, by 2 into G is 9.81 meters per second square, and D is the diameter 0.25 meters here. And substitute all the values in the, this is called Dorsey equation, sometimes it may call Dorsey, and it is also called Dorsey-Viscosky equation, both are same. So Hf is equal to Flv square 2Gd is Dorsey's equation. So use, he has given Dorsey formulae. So when you substitute all the values, the Hf is equal to 1.182 meters. Now take Chayes equation. Another one he has given Chayes equation. V is equal to C root RS and C is equal to 55. C is equal to 55 here. And what is hydraulic mean radius? So hydraulic mean radius is A by P. So in this equation, the value of R is equal to A by P. So A is the area of the cross section of the pipes. It is a circular pipe here, and P is the wetted perimeter. Pipe is running full. And you can take area, circular pipe, pi d square by 4 by pi d. So R is equal to d by 4. So the diameter is 25 centimeters. So the R is equal to 0.25 by 4. R is equal to A by P. A is pi d square by 4, and this is pi d. So R is equal to d by 4, where d is 0.25 meters. Then yes, S is the slope here. S is the slope here, which is equal to Hf by L. So Hf is not known. It is required to find out head loss due to friction by L, length of the pipe. Length of the pipe is 60 meters here. So in this equation, the velocity V is equal to 3 meters per second. Velocity V is equal to 3 meters per second, and C is 55. C is 55, and R is d by 4, 0.25 by 4, and S is Hf by L. Hf is not known, and L is 60 meters. And you can have, you have all the values except the value of Hf. So from this equation you can find out Hf, which is equal to 2.856. Hf is equal to 2.856. Next problem. Calculate the rate of flow of water through a pipe. Rate of flow of water through a pipe of diameter 0.3 meters due to friction when the difference of pressure head between the two ends of the pipe is 4 meters and which are 400 meters apart. He has given F also 0.036. Rate of flow is discharge. It is required to find out discharge Q. Rate of flow is discharge Q. A into V. So A is pi by 4 d square. We have the diameter here. We have the diameter here 0.3. And V is the velocity which is not known here. Then we have the equation here. Difference of pressure head between two ends of the pipe apart is 5 meters of water. So he has given 5 meters. The head loss due to friction. So the head difference is caused due to head loss due to friction. In other words, the water level difference between two reservoirs, will come to that, is equal to the losses here. The loss is a friction loss. So the water level difference between two reservoirs, that is loss of head between section 1 and 2, is equal to losses here, which is equal to HF here. That's why HF we can take value of H, which is 5 meters here. So now the HF is 5 meters. This is 5 meters. And FLV square by 2ZD, F is the quotient of friction he has given 0.036, F is 0.036, L is the length of the pipe. So length of the pipe is, he has given between two ends of the pipe is 400 meters, the length of the pipe is 400 meters here, and the velocity V is not known, and by 2 into 9.81, and the diameter here is 0.3 meters. So we have the values here, this is 5 meters, all the values are known except the velocity V, so we can find out velocity here. So velocity is equal to 1.429 meters per second, 1.429 meters per second. So you have the velocity, you can find out rate of flow. Rate of flow means discharge. Some of the students, when they ask you to find out discharge, they are giving A into VQ, and when he asks rate of flow, and they are unable to give the discharge. Rate of flow means the flow of water flowing per second. Rate means flow rate means a flow or fluid flowing per second, and as discharge is the volume of water flowing per second, so rate of flow or volume of water or volume of flow or discharge, all the three are same. So then Q is equal to AV. So A is the cross-section area, A is the cross-section area of the pipe, pi by 4 d square, and V is the velocity, which is equal to 0.101 meter cube per second. V is equal to 0.101 meter cube per second. So I can find out the by finding out the velocity. So he has used Darcy's equation here, from them we can find out the velocity. And once the velocity is known here, you can use the discharge equation. This is the continuity equation again. So this is the continuity equation, this is the quotient of friction, this is arrived based on Bernoulli's equation. So the applications of Bernoulli's continuous equation and the losses equations and the head loss due to friction and the Reynolds number, all these are required for doing problems in pipe flow. Very, very important. So we have a break here. So now the time is nearing 11:30 or 11:25. We have a 10 minutes break. And what I suggest you is try to refresh and try to remember the equations I have given so far. For example, I have given the so and so equations here, number of equations here. So the Reynolds number, this VD by nu as that's 2000, Dot's equation, hydraulic radius, Sedgwick formula, Manning's equation, and losses here, head loss due to enlargement and sudden contraction, entrance loss, exit loss, and all these are very much required for continuation of this chapter. So try to remember these equations, very important, and so that you can follow very easily without any issue the subsequent topics. We'll come back in maybe 11:25 before 11:35, and try to refresh and try to be healthy and happy, and we'll continue further after 10 minutes break. Yeah. We'll come back to the discussion again, and we have discussed the losses, etc. Now we'll straight away go to flow through long pipes. Flow through long pipes. So here, just I am taking sketch, not exactly for long pipe, and this is a sketch with different pipes here. Let us say, but we will come to that when the pipes are connected in series and parallel. But for the long pipe, let us say a pipe is there in between, long pipe in between. So when you apply Bernoulli's equation between points A and B, when you apply Bernoulli's equation between points, one equation is continuity equation. We can take continuity equation, Bernoulli's equation for solving the fluid problem in pipes. So now the flow through long pipe, when you consider long pipe between reservoir A and B, so this is a tank here, A, and this is a tank B, a pipeline is connected, you carry water from reservoir A to B. So the issue here is how you are going to analyze here. I will come to that exactly when the pipes are connected in series for this, but long pipe discussion, I am taking this sketch. And H is the head difference between two reservoirs here. This is reservoir A and reservoir B, and H is the head difference. Water level difference between two reservoirs, which is equal to sum of losses. When you apply Bernoulli's equation between A and B, when you apply Bernoulli's equation between A and B, then H is equal to, in other words, H is equal to the water level difference between two reservoirs is equal to sum of losses. I will come to that losses afterwards, sum of losses, but H is equal to sum of losses. Suppose if we have a long pipe here, instead of all these pipes, what are the losses you can expect here? So here we have an entry loss here. Let us say this is only one pipe here, we have friction loss, and here you have an exit loss here. So the value of H, I have considered only three losses here, not the other losses. I will come to that afterwards. But long pipe, when there is only single pipe, and we have entry loss here, exit loss here, and friction loss. So the water level difference between two reservoirs, H, is equal to sum of losses. What are the losses we have? Entrance loss, exit loss, and sudden contraction, whatever it is, all the losses put together, that will be equal to head. That is water level difference between two reservoirs. So this is very, very important equation. Try to remember. And while you are doing it problems, so straight away I will be taking H is equal to the sum of losses. So that you can obtain from the Bernoulli's equation. Apply Bernoulli's equation between points A and B. You can get that the value of H, capital H, is water level difference between two reservoirs is equal to sum of losses. That is one equation. The other equation is discharge. Discharge is same. Discharge is same. So now, okay, so this is the water level difference between two tanks is equal to sum of losses. Now the pipes are connected in series. Let us have the discussion now. The pipes are connected in series. So sometimes you may not have the pipes. Sometimes may not have the pipes. You may have a different pipes here. You may have a different pipes here. Then how will you analyze this problem? So once again, one equation is the water level difference between two reservoirs is equal to sum of losses. And the second equation is, suppose if you see here, we have three pipes here. The single pipe is not available. So we have three pipes here. The pipe 1 length is L1 and diameter is D1 and friction is F1 and the length L2, diameter D2 and the friction F2 and length L3, diameter D3 and the velocity is V3 and the friction is F3. So F is the coefficient of friction. This is the coefficient of friction here, V1, V2 with their velocities and L1, D1, L2, D2 and L3, D3 are the length and diameters for pipe 1, pipe 2, pipe 3 and F1, F2, F3 are the coefficient of frictions for pipe 1, pipe 2 and pipe 3. This is general data he has given and we have two equations here. One is the continuity equation, whatever the quantity of water which is entering here, the same is exiting here. So the water which is flowing through the pipe is equal to the water which is exiting in the pipe here. So here Q is equal to the equation 1 is equal to Q is equal to Q1 is equal to Q2 is equal to Q3. So Q1 is the quantity of water which is flowing through the pipe here and Q2 is the quantity of water which is flowing through the pipe here and Q3 is the quantity of water which is flowing through the pipe here. Pipe 3, pipe 1, pipe 2 and pipe 3. What is the relation between Q1, Q2 and Q3? So the velocities are not equal, the diameters are not equal, but the quantity of water which is flowing through the pipe is same, even though the pipes are of different diameters and lengths. That is the continuity equation. So the continuity equation is equal to A1 V1 A1 V1 is equal to A2 V2 is equal to A3 V3. That is one equation. Then the second equation, important equation. With the help of those equations, you can solve the problem when the pipes are connected in series. Series is 1 by 1. Series is 1 by 1. Parallel means that I will come to that afterwards. So now the H is equal to sum of losses. What are the losses here? So here, so the first loss you can see here, we have entry loss here. Again along the pipe length, what is the loss here? We have friction loss. So here entry loss, here friction loss. Again if you see here from here to here, there is sudden contraction. So we have entry loss here, friction loss here, we have a sudden contraction here. Head loss due to sudden contraction. So head loss due to sudden contraction, it is required to take here. That part is over. Again, we have friction loss here. Again, from here to here, there is enlargement. Head loss due to sudden enlargement, not gradual. This is sudden contraction, this is sudden enlargement. Need to consider sudden enlargement here. And again, we have friction loss here for the pipe 3. Friction loss for the pipe 3. Again, we have exit loss here. These are the losses here. These are all very simple, provided you know what are the equations of losses and what are the equations for minor losses, what is the equation for major loss, all these things, Bernoulli's equation, everything is simple, provided you know all those equations, and this is the application of those equations here. Now, so the value of H, here the loss here is entrance loss. So what is entrance loss here? So entrance loss is 0.5 V1 square by 2Z. Entrance loss is actually the 0.5 V square by 2Z. V is the velocity of the water which is entering the pipe. So actually the equation is 0.5 V1 square by 2Z. So this is 0.5 V1 square by 2Z entrance loss, and V is the velocity of the water which is entering. So 0.5 V1 square by 2Z is the entrance loss. Then for the pipe 1, the friction loss. So FL V square by 2ZD. So FL1 V1 square by 2ZD1. So see here, first is entry loss. So entry loss is 0.5 V1 square by 2Z. Then friction loss. So FL1 V1 square by 2ZD1. Then, so now we are here. So then, head loss due to sudden contraction. So the students are taking, some of the students they are taking, no doubt they see the equation is 0.5 V square by 2Z. then what is the velocity you need to consider? So velocity after contraction. So here you need to consider, no doubt we have a head loss due to sudden contraction. The equation is 0.5 v square by tg, and that velocity is velocity after contraction. So need to take v2, not v1. So the head loss due to sudden contraction is 0.5 v2 square by 2z, 0.5 v2 square by 2z. That is head loss due to sudden contraction. Again, head loss due to sudden contraction, HSC, then HF2. So HF2 is head loss due to friction for the pipe 2. HF2 is head loss due to friction for the pipe 2. And what is HF2? So HF2 is equal to F2 L2 V2 square by 2z d2. F2 L2 V2 square by 2z d2, that is a head loss due to friction for the pipe 2. Then we have a HL, head loss due to sudden enlargement. Head loss due to sudden enlargement here. So from here to here, there is head loss due to sudden enlargement. The equation for head loss due to sudden enlargement is V1 minus V2 whole square by 2z. Then in place of V1 and V2, we have V2 and V3 here. So the velocity before enlargement is V2 and velocity after enlargement is V3. So V2 minus V3 whole square by 2z, that is head loss due to sudden enlargement. And again friction loss here, this is head loss due to sudden enlargement, and friction loss for the pipe 3 and exit loss. These are the losses here. Entrance loss, friction loss for the pipe 1, head loss due to sudden contraction, friction loss for the pipe 2, head loss due to sudden enlargement, friction loss for the pipe 3 and exit loss. These are the losses here. So here head loss for the pipe 3, HF3, so which is equal to FL3 V3 square by 2GD3, FL3 V3 square by 2GD3. So D is the diameter and L3 is the length, V3 square is the velocity square by 2GD3. And the final one is exit loss. So exit loss here, it is the velocity with which the water is exiting here. So exit loss is V square by 2z. In place of V, you need to take V3 because this is the velocity of the water which is entering here, exiting here. So this is V3 square by 2z. So that is the equation here. Very, very simple, provided you understand the equations and the way you have to deal by taking those equations for solutions. So sometimes he may give you the minor losses are neglected. So sometimes he may give neglect minor losses. So in that case you can take only friction loss. So for which H is equal to HF1 plus HF2 plus HF3. Suppose if you neglect minor losses, the major loss is friction loss. So H is equal to HF1, HF2, H means this one. So the head water level difference between two reservoirs, this H is equal to HF1, head loss due to friction for the pipe 1, head loss due to friction for the pipe 2 and head loss due to friction for the pipe 3. So those three are the losses here. Sometimes we may ask you to neglect minor losses, need to consider only friction losses for pipe 1, 2 and 3 and equate to H here. Next, equivalent pipe. Very important, he has given in the gate problems also, I have seen. So when all the equivalent, what is it meant by equivalent pipe? So equivalent pipe is when all these pipes are connected, by a single pipe. So now you see here, these are the three pipes which are having different lengths and diameters. So instead of three pipes, for example, a single pipe is there of length and diameter, length is L and diameter is D. So if it is replaced, if all the three pipes are replaced with a single pipe having length L and diameter D, so what is the relation between L, L1, L2 and L3? So we have three pipes here which are connected in series of length L1, L2 and L3. All the three pipes are replaced by a single pipe of length L, then what is the relation between L1, L2, L3? So L is equal to L1 plus L2 plus L3. So the length of the pipe is same. Length of the pipe is equal to different lengths of different pipes. So L is equal to L1 plus L2 plus L3. Then he has asked to find out the diameter of a single pipe of length L and diameter D in terms of D1, D2, D3, in terms of L1, D1, L2, D2, L2, D3. Simple. So that equation is called diffusion equation. So for that the procedure is, so find out head loss deflection for the pipe 1, find out head loss deflection for the pipe 2 and find out head loss deflection for the pipe 3. These are the losses here. Again use a separate pipe, use an equivalent pipe. Equivalent pipe is a pipe which is replacing all the 3 pipes. Equivalent pipe length is L and diameter is D. So for the equivalent pipe, find out the head loss due to friction. So HF. So you can take head loss due to friction for the equivalent pipe is equal to sum of friction losses for 3 pipes. So HF is equal to HF1, HF2 and HF3. So head loss due to friction for the pipe 1, FRV square 2GD is equal to HF1. HF1 is F1 L1 V1 square by 2GD1 plus HF2, F2 L2 V2 square by 2GD2 and HF3, F3 L3 V3 square by 2GD3. So sum of head loss due to friction, which is equal to head loss due to friction for the single pipe. So HF is equal to HF1 plus HF2 plus HF3. So then equating those losses, the final equation is L by D5, L by D5. This is the famous equation, Dippert's equation here. So this is L by D5, which is equal to L1 by D15, L1 by D15 plus L2 by D25 plus L3 by D35. You have a plus sign is here. Plus sign. So the equation is L by D5 is equal to L1 by D15 plus L2 by D25 plus L3 by D35. That is Dippert's equation. And equivalent length losses, equivalent pipe, the losses are whole losses are HL, and which is equal to sum of the losses of 3 pipes. So because friction loss is major loss, you can take HF is equal to HF1 plus HF2 plus HF3, and length L is equal to length of equivalent pipe L is equal to L1 plus L2 plus L3. And the resulting equation, if you use this equation, the resulting equation is L by D5 is equal to L1 by D15, L2 by D25 plus L3 by D35. The simple equation that is called Dippert's equation. This is very, very important. Any examination, there should be obviously a question on Dippert's equation. Now the previous case is the pipes are connected in series. Pipes are connected in series. Now the pipes are connected in parallel. Earlier we have discussed the discussion that is pipes connected in series. Now the pipes connected in parallel. So then what is the solution here when the pipes are connected in parallel? This is the case. So when the pipes are connected in parallel, so this is the main pipe here, this is the main pipe here, which is divided into 2 pipes, main pipe which is divided into 2 pipes, and again joined together here, again joined together in a single pipe. So these 2 pipes are connected parallel, not one by one, simultaneously. So the quantity of water, so this has taken here Q2 and Q1 also. So the pipes are connected here, when the pipes are connected in parallel, so these 2 are connected and joined together as a main pipe. When the main pipe divides into 2 parallel pipes and again joined together in a single pipe, so this is called the pipes in parallel. The pipes are connected in parallel. So then how will you do analysis for this? This is also simple. So the continued equation, use the continued equation carefully here. So normal continued equation is Q is equal to Q1 is equal to Q2 is equal to Q3, but that is not correct here. Why? So the quantity of water flowing through the pipe 1 is Q1, for which the length of the pipe is L1, diameter is D1 and velocity is V1. And Q2 is the length of the pipe is L2 and diameter is D2 and V2 is velocity here. This is branch pipe 1 and branch pipe 2. The pipes are connected in parallel. Then what is the relation between Q, Q1 and Q2? So whatever the quantity of water which is coming here, that is Q2, and the quantity of water which is coming here is Q1. So both Q1 and Q2 combined together and joined together and flowing the quantity which is equal to Q. So the equation is Q is equal to Q1 plus Q2, not Q is equal to Q1 is equal to Q2. Some of when they are taking Q is equal to Q1 is equal to Q2, not correct. Q is equal to Q1 plus Q2, branch pipe 1 and branch pipe 2. So that is one equation. The discharge equation is now Q is equal to quantity of water which is flowing through the pipe 1 plus quantity of water which is flowing through pipe 2. What is the second equation here? We have two equations. One is discharge equation, the other one is the equation based on Bernoulli's equation, the sum of losses. So the second thing here, if you see here, the losses in the pipe 1 and loss in the pipe 2, the second equation is, so you can make equal or you can equate losses in pipe 1 is equal to loss in pipe 2. Neglect bend losses, neglect minor losses, only take frictional loss as a major loss here. So the second one is take frictional loss HF1 which is equal to HF2. So the first equation is Q1 plus Q2 is equal to Q, and second equation is, as you have neglected minor losses, minor loss including bend loss. So because you can see here this is a bend, you have bend here, you have bend here. Neglect all the other losses, we have only frictional loss is a major loss here. So the head loss due to friction for the pipe 1 is HF1 and head loss due to friction for the pipe 2 is HF2. So you can take HF1 is equal to HF2. HF1 is FL1, FL1, V1 square by 2Z D1, which is equal to FL2, V2 square by 2Z D2. And friction loss for the pipe 1 is pipe 2, and Q is equal to Q1 plus Q2. So see here, so the first equation is Q is equal to Q1 plus Q2, and the losses in pipe 1 is equal to losses in pipe 2. In other words, you can take HF1 is equal to HF2. Then the other one is siphon. This is the siphon pipe. Siphon is a bent pipe. Siphon is not a different, don't think that siphon is somewhere different, something different from the pipe, other pipes. So siphon is also a bent pipe. So siphon is a bent pipe here. If you see here, there are two reservoirs A and B, reservoir A and reservoir B. And when these two are separated, when these two are separated by a hill, there is an obstruction here, let us say. So in between reservoir A and B, there is an obstruction. Then what will you do? So you cannot lay a direct line here. So you cannot lay a direct line between A to B. There is an obstruction. There is a hill type of structure here. There is an elevated ground here. You cannot lay a direct pipeline between A and B straight away. So as there is a elevation here, as there is obstruction here, this is obstruction here. So you can run a pipeline taking around the obstruction, and so that it reaches the water from A to B here. So from A to B, as there is obstruction here, so we have to use a bent pipe which carries water from A to B. A to B here. So this is A here and this is B here, reservoir A and B. And this is the topmost point is called summit, and this is siphon. This is siphon, and the topmost point is called summit. Summit is the highest portion of a siphon. Sometimes he is asking what is the height of the summit. The height of the summit is small h here. So small h is different and capital H is capital H is the water level difference between two reservoirs. So from here to here is capital H. So this is the water level surface of the reservoir A, this is the water level surface of the reservoir B, and if you take water level difference, this is the capital H. Some of the students are confusing with capital H and small h. Small h is different. Small h is the height of summit with reference to the water level surface of reservoir A. With reference to the water level surface of reservoir A. So then, what is this here? From here to here, from the inlet to the summit is called inlet leg. Inlet leg. I-N-L-E-T, L is the leg. Inlet leg. So the inlet leg is the pipe portion from reservoir A to the summit, and from here to here, this is called outlet leg. Outlet leg. Outlet leg is, it is from the summit, the pipeline from the summit to the reservoir B. This is outlet. So because the water is entering here, this is inlet and this is outlet. So inlet leg and outlet leg. So the terminology here is inlet leg, outlet leg, and summit and siphon. You need to remember all these things. And then how will you do analysis for this? So the first equation, the water level difference between two reservoirs from here to here, which is sum of losses here. So the water level difference, that is capital H, is equal to sum of losses here. What are losses here? So capital H is from here to here, sum of losses. Here we have entry loss here. Here we have entry loss here. And we have friction loss here. Neglect bend losses. So we have a friction loss here. Along the pipeline we have a friction loss here. The length of the pipe, let us say length of the pipe is L1. L1 means the pipe length around this portion, inclined portion. This is L1 here. So we have friction loss for the pipe length L1 here, and we have exit loss here. So the capital H. So the first one to solve the siphon problem is the capital H. Capital H is water level difference between two reservoirs. Water level difference between reservoir A and B, that is capital H, which is equal to sum of losses. The losses are entry loss here. Entry loss is 0.5 V square by 2Z, and exit loss is V square by 2Z, and friction loss is F, length of the siphon, FL V square by 2GD. So with the help of this you can find out the unknown. What are the unknown? Then sometimes he is also asking the height of summit. So to know the height of summit, you can apply Bernoulli's equation at A and Bernoulli's equation at C. So you can apply Bernoulli's equation at A and Bernoulli's equation at C, so that you can find out the height of summit. Straight away apply Bernoulli's equation at A and apply Bernoulli's equation at C, and this becomes a datum. Suppose if you take datum Z1 0 and Z2 will be H, so that you can find out the value of H here. So for finding out height of summit, just apply Bernoulli's equation for the reservoir A and Bernoulli's equation for the summit, so that you can find out the unknown. So because the datum here is Z1 is equal to 0 and Z2 is from here to here, Z2 is equal to H. So height of the summit can be known in the help of the equation. Only two equations. One is H is equal to sum of losses. The second one is apply Bernoulli's equation between A and C, so that you can find out the value of H. So one is sum of losses is siphon, sum of losses is entry plus friction loss plus exit loss, and the application of Bernoulli's equation to find summit height. Then we have a Another important object type, hydraulic gradient line, total energy line. So what is hydraulic gradient line and what is total energy line? So hydraulic gradient line is the line which gives a sum of pressure head and datum head, of a flowing fluid in a pipe with reference to line. The hydraulic gradient line, name itself very clear, hydraulic gradient line, it is sum of pressure head and datum head. So we have three heads, if you remember, we have three heads. The Bernoulli's equation, what is Bernoulli's equation? Bernoulli's equation is sum of pressure head, velocity head and datum head is constant. So take three heads and suppose if you take pressure head and datum head, so the sum of pressure head and datum head is called piezometric head. Sum of pressure head and datum head is called piezometric head. So that means the Bernoulli's, the hydraulic gradient line is a line which gives sum of pressure head and datum head for the flowing fluid in a pipe. Important object type, that's why I am stressing. Other words, you can also tell that hydraulic gradient is a line which gives the piezometric head for different points in a flowing fluid in a pipeline. So the piezometric head is P1 by W plus Z1 and also Pt by W plus Z2 at different points 1 and 2. And the second one is total energy line. Total energy line, name is very clear. Total energy consists of all the heads. Total energy, we have pressure energy, dynamic energy and datum. So if you take a pressure head, velocity head and datum head, so the sum of pressure head, velocity head and datum head, it is defined as the line which gives a sum of pressure head, datum head and velocity head at different points of a flowing fluid in a pipeline. Simple, hydraulic gradient line is you can also call it as a piezometric line because it is a line which is giving piezometric heads. The total energy line, it is a line which is giving total energies. It is a line which is giving total heads. Simple difference, hydraulic gradient line, total energy line. Hydraulic gradient line is piezometric line, total energy line is also total head line. You can easily differentiate. Now hydraulic gradient line and total energy line. How will you draw, how will you get hydraulic gradient line and total energy line? For a simple case. The pipeline is horizontal. Let us say this is the pipeline which is horizontal. So if it is vertical, we have datum heads also. And this is the pipeline. This is the tank here, which is this is the horizontal pipeline which is carrying fluid from reservoir A to the open. Coming to the open. And for this case, how will you consider hydraulic gradient line and total energy line? The procedure is very simple. So hydraulic gradient line. This is the hydraulic gradient line. So you can select, for the drawing hydraulic gradient, select some points and let us say the point 1 here and point 2 here. Let us say 2 points you consider are different points along the center line of the pipe. So consider different points along the center line of the pipe. Let us say this is point 1 and install piezometer here, and point 2 install piezometer here, and point 3 install piezometer here. And this you can consider the datum line. This is the horizontal line, so that the Z1 is equal to Z2 is equal to Z3. So all the datum heads are same here. So install piezometer here and find out the height of rise here, and for this piezometer find out the height of rise here, So install piezometers at different points along the center line of the pipe. Piezometer, as you know, it is required to find out pressure at a point. So piezometer discussion, it is a fundamental chapter, pressure chapter. So if you did not remember piezometer, then you cannot able to understand this problem, this issue. So you can install piezometer. Piezometer is a pressure measuring instrument which is required to find out the pressure at a point. So for finding out the pressure at a point, or pressure head, you can install piezometer here and find out the height of rise. So the pressure head is equal to height of rise here. and the pressure head is equal to, if you have a piezometer here, find out the height of rise. Height of rise is equal to pressure head. So now you have the value of P1 by W here and P2 by W here and P3 by W here. All the pressure heads are known by installing piezometer, by measuring corresponding heads. Then all these are known, so that you can, now we have a pressure head here and datum head. Datum head Z1 is same. So P1 by W plus Z1 is this line here. This point here, we have a point here of P1 by W plus Z1. Again, you draw here, this is the P1 by P2 by W, piezometer head, plus Z2 here. And this is a line which is giving sum of pressure head and datum head. So I can install a piezometer to get pressure head, and datum head is Z1 is same here. And we have different points here. The point 1 is pressure head and datum head, and pressure head and datum head, and join all these points, we can get a straight line, that is hydraulic line. And the last point which joins here, so because if you take the point here, this is the point here and exactly here, because it is coming out, we have atmospheric pressure here, this joins right away here, the hydraulic line which joins the last point here, and the first point is not well defined. First point is not well defined because of the formation of vena contract, etc. Vena contract, as you know, vena contract is the point at which the jet has minimum cross-section area. In the last class we have discussed that. So the first point is not well defined, but the last point is defined here. It joins the water surface here, and this is the point which is giving sum of pressure head and velocity head. Pressure head and datum head. And then total energy line. So the total energy line, name itself is clear. This is giving pressure head and datum head, and this is the velocity head. If the pipe is horizontal, the velocity is also same. So you can draw another line with V square by 2Z. So we have pressure head and datum head up to here, and again we have only velocity head. So velocity head is V square by 2Z. So this point we can extend to the top, and this magnitude is equal to V square by 2G, as velocity is same, and we have draw a parallel line such that the distance between these two is V square by 2G, velocity head. You can get a total energy line also. Again, the first point here, it is defined now. This first point is defined. So what is the level difference between this one? This is entry loss. So this is entry loss. So from here to here, you can draw a point here. This is 0.5 V square by 2Z. So velocity of the water which is entering here is V. So this is 0.5 V square by 2Z. 0.5 V square by 2Z here. And from here to here, this is a friction loss. You can take friction loss here. Again at the end, this is also very clear. This is exit loss. Exit loss is V square by 2Z. So this is V square by 2G, and this is 0.5 V square by 2G, and this is friction loss. So very easy to draw hydraulic line, total energy line, provided you know the fundamentals. So this is entry loss is 0.5 V square by 2Z, and exit loss is V square by 2Z. This is also V square by 2Z, and friction loss is HF. The sum of losses are entry, exit plus V square by friction loss. Entry loss plus exit loss and friction loss, and you can draw the TL very without any problem, with comfortable, you can draw total energy line. So here this is hydraulic line P1 by W plus Z1, and this is V square by 2G or V1 square by 2G. As velocities are same, we are getting the same line, parallel line. Then the other one is branch pipe. So this is the branch pipe. If you know this branch pipe, you can able to solve any type of fluid flow problem. Then what is branch pipe? When three or more pipes are connected, by means of pipes. So here, when we have three pipes here, this is three reservoirs here, reservoir A, reservoir B, and reservoir C. And three reservoirs are connected by three pipes here. This is pipe 1, pipe 2, and pipe 3, having junction. This is called junction. When three pipes are connected, with the help of the junction. One sometimes may have two junctions here. When three or more reservoirs, when three or more reservoirs connected by means of pipes, by means of pipes, having one or more junctions, the system of this system is called branching system, and the pipes are called branch pipes. So suppose if you see here, we have three reservoirs connecting the help of the pipes having one or more junctions. So this is one junction here. At the junction, the velocity is 0. So the these pipes are called branching pipes, and this is called branching system. Then how will you do this problem? Simple way of doing the problem here. So the first one is when three or more reservoirs are connected by pipes having one or more junctions, which is called a branching system, and the pipes are called branching pipes. Then we have the equation here. The first one is discharge equation. Let us say the length of the pipe 1 is L1 and diameter is D1, and HF1 is head velocity friction for the pipe 1, and V1 is the velocity of the water in pipe 1, and ZA is the datum line for pipe A, and ZB is the datum line for the pipe B, pipe B, and reservoir C, ZC is the datum line for the reservoir C, and ZB is the datum line for reservoir B, and ZA is the datum line for reservoir A, ZA, ZB, and ZC are datum heads for reservoir A, B, and C. And we have V2 here. V2 is the velocity of the water which is flowing through the pipe 2, and length of the pipe 2 is L2, and diameter is D2, and HF2 is head loss due to friction. HF2 is the head loss due to friction. And L3 is D3, HF3. phone చేస్తుంది వాడి ఒక నిమిషంలో చేస్తాను. So HF3 FL1 V1 square by 2G D1 friction loss for the pipe 1, and friction loss for the pipe 2 is FL2 V2 square by 2G D2, and friction loss for the pipe 3 is HF3 FL3 V3 square by 2G D3. And this D is the junction for which the datum head is ZD. So these are the notations here. Then how will you analyze? How will you solve these issues here? So one is use discharge equation. The other one is use Bernoulli's equation. With the help of Bernoulli's equation, discharge equation, we can able to solve any number of problems here. So the first one here is discharge equation. So the Q1 is the quantity of water which is flowing through the pipe. Q1 is the quantity of water or the discharge for the pipe 1, and Q2 is discharge for the pipe 2, and Q3 is the discharge for the pipe 3. Then this Q1, so water is the water which is coming from reservoir A is equal to Q2 plus Q3. So the equation for is, so I can take a Q1 which is equal to Q2 plus Q3. There's one equation. We have one equation of discharge. What are the quantity which is entering here, which is going to B and C? So Q1 is equal to Q2 plus Q3. That is one equation. And second equation, you can write Bernoulli's equation at point A, Bernoulli's equation for reservoir A and B position. So I can write Bernoulli's equation in A and B. So one thing is, we have assumption that the velocity of the flow at junction is 0. So I can write the Bernoulli's equation comfortably without any problem. So I can apply Bernoulli's equation between A and B and take that the velocity of the water at junction is 0. and the loss, you consider only loss here, that is the loss is head loss due to friction HF1, neglect minor losses here, entrance loss, exit loss, etc. Only major loss is friction loss. So the loss here is HF1 when you use Bennett's equation between A and B, and the datum is ZD here for D, and the datum is ZA here for this. And you can write the Bennett's equation between A and D, and taking ZA and ZD are datums, and the velocity of the water D is 0. That is one equation. Second equation, one equation is discharge equation Q is equal to Q1 plus Q2, and second equation is between Bennett's equation A and D, and the third equation is Bennett's equation between D and B. Write Bennett's equation between D and B. So at D again, the velocity of the water at junction D is 0. Again, the velocity of the water at reservoir B is ZB. The datum head is ZB. So write Bennett's equation between B and D, and loss here is HF2. That is the third equation here. HF2 FL2V2 square by 2GD2. You can write, you can know the friction loss here for the pipe 2, and write Bennett's equation between D and B. We have a ZD here, we have a ZB here, and the velocity of the water junction is 0, and HF2 is the head loss due to friction for the pipe 2. You can simply write the equation between D and D, that is the third equation, and the fourth equation from D to C. Fourth equation from D to C. Again, write Bennett's equation. Write Bennett's equation between D and C. Write Bennett's equation between D and C. Again for D at junction, we have a datum head ZD here, and the velocity is 0 here, and the datum head ZC is here, and we have a head loss due to friction HF3. Head loss due to friction HF3 is there. So you can write the equation. We have 4 equations here, and we can find out Q1, Q2, and Q3, and also directions, datum head sometimes. So first equation is Q1 is equal to Q2 plus Q3. The second equation based on Bennett's equation between A and D, and the third equation is based on Bennett's equation between D and B, and the fourth equation is based on the Bennett's equation between D and C. So with the help of all these equations, we can solve any type of fluid problem, any type of fluid problem. We can do analysis of pipe flow. All this discussion is very, very important. All this discussion is very, very important. And these are all required for solving not only problems, general problems. In the GATE examiner is giving 1 mark question, 2 mark question, 5 mark question, etc. The equations and the relevant theory I have discussed now, today, and which is useful in the GATE examination. Also, while discussing the solutions of the GATE questions, it is required for you. So that's why I invite or request, I suggest you to study the theoretical background of this entire chapter, so that it will be easy for us, for you to understand the GATE questions and the relevant solutions. No worry, very simple, provided you have, you know the equations, you know the relevant discussion from the last classes. If you follow all these things, and you can easily get answers for the questions here. We'll take up the slide problems also tomorrow. And again, thank you very much, the student friends. And today we have discussed at length about and some problems on analysis of pipe flow, which is very, very important chapter, and which is not only important, it is also required for particularly GATE examination. So this entire chapter we have a number of questions, and in some of the textbooks this chapter has covered in 3 chapters: laminar flow, turbulent flow, analysis of pipe flow. All the 3 put together I have covered in 1 chapter. Broadly, analysis of pipe flow, it covers laminar flow, turbulent flow, and relevant equations, and also pipe analysis. All these 3 in 1 chapter. Entire theoretical background I have covered, important discussion I have made, and please make a study on that, and please try to be conversant with all the formulae which was given today, and so that it will be useful for tomorrow. And thank you very much for patient hearing. And again, tomorrow I will meet you in online class tomorrow at 10:30. Thank you all. And tomorrow we'll be dealing the objective questions of this chapter and also problems. And if time permits, we'll start the analysis of the notches and R5s. Otherwise, we'll take some object type, or better start notches and R5s, and the balance day after tomorrow, and afterwards the boundary layer and the lift and drag. This is all the schedule and the planning of the GATE online classes. And thank you very much. And thank the organizers also for their help in taking up this class. Thank you.